Uh, this is a good news, bad news week. Mostly bad news, so I think we ought to start out with the good news first. First of all, we have a GSI in this class whose name is Ryan Kelly. Now, what do you suppose his country of origin is? And do you suppose maybe this is his big day? He's sitting back there with a shirt full of shamrocks on. So anybody else here who counts himself as Irish? Okay, we got a few more. Well, congratulations to all of you. That's good news. The other good news is that spring break starts real soon, doesn't it? And I bet we're all just ready for it. And considering what's been going on lately, I suppose maybe we're more ready for it than ever. I've been giving you little updates on what's going on in Libya. And the general news, because this seems to be a historic time. Normally I wouldn't be bothering to tell you about the news, but it seems like such a historic time. And think back a little bit on what's going on in January. You had the first of the Arab revolts in Tunisia, and they got rid of their dictator. And then Egypt, and they got rid of their dictator, and it was being called the Arab Spring, as if everything was getting bright. Then we've been following what's going on in Libya. We'll come back to that in a moment. And Libya was all over the, 2 or 3 pages on the inside of the New York Times every day, all over Al Jazeera and the BBC and everything else. You read about Libya now? Nope, almost nothing. And the reason, of course, is that there was a truly catastrophic earthquake in Japan that generated a tsunami. And if I were superstitious, I'd be feeling guilty for having given you a lecture about tsunamis a week ago. But boy, I sure couldn't have imagined what was going to happen and what it was going to be like. Latest confirmed death toll in Japan, around 13,000, with Lord only knows how many more missing and unaccounted for. No idea what the final toll will be. And even that's being pushed out of the news now by the nuclear reactor episode that they're having over there. So if any of you are following it right now, this will be a month that people won't forget for quite a while. I can hardly bring myself to talk about Libya. Ryan gave me a nice little synopsis at the beginning, so I'm going to ask him to tell you what's going on in Libya right now. Got the microphone? Yeah.
Wow. Great. Well, I didn't anticipate being in charge of this, so here goes nothing, I suppose. When we kind of last tuned in, the rebels were doing fairly well as of kind of a week ago, or a week and a half ago, and then Gaddafi seems to have rounded up enough people and mustered enough planes that the rebels have kind of been on the run since then. And all those maps that we were looking at with the kind of primary rebel stronghold being in the east of the country and Gaddafi's stronghold just being right in Tripoli, really, it seems like the chunk of the country that is under Gaddafi's control has kind of grown steadily eastward towards Benghazi from Tripoli. And some of the towns that we kind of focused on have been in the news if you read the paper or the virtual paper online, which incidentally the New York Times is finally shutting down its site for free next week. So it's March 28th that you're going to have to start paying for it. So get it while you can. Huge wealth of information. You can kind of follow this stuff, but in any case, Gaddafi has kind of been increasingly brutal in bombing people and strategic depots and whatnot. And so it seems like the window for one of the foreign policy things that was being discussed for the U.S. was to implement a no-fly zone. And I am certainly no expert in any of this, but my understanding of what a no-fly zone entails is kind of sending enough U.S. and allied forces there to make sure that there aren't Libyan bombers, Libyan planes flying in the country. And what that would do would be preventing the kind of most devastating damage that Gaddafi's doing to the country by doing away with his airplanes. And so the implication is that we would shoot down Libyan airplanes in Libyan airspace. So this is not something that not something to be taken lightly, and certainly nothing the Obama administration was taking lightly because of obviously our recent history of involvement in the area. I think the overwhelming foreign policy concern for the U.S. is staying out of trouble in yet another Muslim country. But on the other hand, there is some moral force to the argument that Gaddafi needs to be stopped from killing his own people. So that's the kind of crux of the matter. But as time has gone by, Gaddafi has kind of gotten more and more and more territory back, seems to have consolidated his strength, and the window for in which a no-fly zone would have been a sufficient policy tool seems to have passed. And so the question now is, can we justify more substantial military involvement in the country? And it's not something we want to do, clearly. But there was a statement by the Arab League, which is an organization of 22 Arab nations. Actually, is kind of the list of nations that have been having uprisings and various demonstrations in the last month or so. But the Arab League made a statement on Saturday that seemed to be in support of some intervention in Libya, which kind of gave a lot of force to kind of put wind in the sails of a U.S.-sponsored, I believe U.S.-sponsored resolution before the UN Security Council. What all of this is cover for the U.S. to not be seen as going alone into another Muslim country and having any sort of military adventures there. And so I think what the Obama administration wants is for the UN Security Council to pass a resolution, have a set of allied forces kind of contain Gaddafi, but it's not exactly clear what that would look like to me. There's only one Arab state that's a member of the Security Council at the moment, and that's Lebanon. And I don't know a ton about the politics of what historically Lebanon has close ties to Syria and to Iran, which is the kind of major power, one of the major powers in the region. And it's not clear to me what the relationship of Lebanon, Syria, and Iran is to Gaddafi and Libya itself. So that is all playing out at the moment on the floor of the UN. In the Security Council, at least. And I don't know, do you know, John, what the prognosis is for that?
I haven't been paying attention to the radio.
Yeah. So that's kind of the update. Oh.
Providing military force for absence. So those are the first countries to do it.
So Denmark's committed to doing something, yeah. So I think it's really an open question about where this is one of those extremely tough foreign policy questions, kind of where the moral right is and the strategic right over time, and we'll see what happens. So that's the best I can do.
Thank you, Ryan. That was just excellent. As historians, we might realize, and I've said this before, that 20 years from now, 50 years from now, 100 years from now, there will be historians writing PhD theses and books about this, I suspect, if books still exist. And they will really know what was going on. But we don't know what's going on. Imagine you were President Obama right now, and you have to decide, are you going to go in there and do something, or are you not? And I'm not privy to what's going on in the White House right now, but you can sort of picture some of the considerations. So if we do go in there, as Ryan said, that would be a third Muslim country that we would be having military presence in. Do we want to do that? Is that a good thing? On the other hand, maybe this is the one case right now where we would be respected by the Arab world for stopping somebody who is killing Arab citizens, right? On the other hand, suppose that we go in successfully and and get rid of Gaddafi, and the rebels take over. Nobody really knows who these rebels are. We know that the basic unifying thing is hatred of Gaddafi, and you could understand that after 42 years of iron-handed, iron-fisted rule. But who knows what would take over? Could Libya just degenerate into perpetual civil war and we would be part of it? Or would it be the first true Arab democracy, really true democracy, and we would hold up our heads and they would be so grateful that we had taken out Gaddafi? You don't know what's going to happen. If we sit on our hands right now, which is pretty much what has been happening so far, then think about people all over the Muslim world who will look at look at President Obama's speech in Cairo last year, in which he was essentially saying, we support movements of democracy and freedom in the Arab world. And they would say, well, that's all just talk, because all the United States wants is a stable country that's pumping out gasoline so we can continue to use gasoline. An awful thing to have to decide. I guess that's why he gets paid the big bucks, but it's a grim thing to have to decide, and it has been making me think more and more about how isolated historians are when they decide what happened from the fog that was going on while it was really happening. It's also made me think a little bit about what we judge to have been good outcomes and bad outcomes in history. I mean, I think there are some things that almost everyone now would agree was a really bad thing, like Hitler coming to power and starting the Second World War. There are things that are widely viewed as very good, like the success of the civil rights movement in this country in the 1960s. I'll tell you one that's surely good, and that's the fact that there never was a full-scale nuclear war during the Cold War period. I mean, we got out of that by the skin of our teeth. So maybe there's a really bad one is Hitler, a really good one is no nuclear war, and there are all of these ones that you have a really hard time deciding. For example, what about the decision to drop the atomic bombs on Japan? In a sense, that was a terrible thing to do, but as a cold-hearted calculation of benefits and losses, and they were expecting 1 million people to die in the projected American invasion of Japan that was going to be necessary to finish the Second World War. 2 atomic bombs, 2 cities lost in a horrible way, and probably 1 million people didn't die who would have died otherwise. How do you judge that? It's very difficult to make any sort of a judgment about these things. And I think that's what's going on right now in the Arab countries, and especially in Libya. We don't know how we're going to look back on this in the long run and how we're going to judge it to have been. Another thing that has been crossing my mind lately is just thinking about revolts and rebellions. So sometimes they're successful, like ours against the British in 1776 was successful, and we have the country we do as a result of that, right? And at the end of the Cold War, the Eastern European countries successfully freed themselves from the Soviet Union. So those were successful revolts. And whether you judge them to be good or bad kind of depends on who you are and where you live and what your circumstances are and what your mindset is. But nevertheless, you can say those were 2 successful revolts. There have been other revolutions that have not been. Are you aware of the year 1848? Okay, think about that. It happened to be the year that gold was discovered in California, and the gold rush came the next year. But in Europe, it is known as the year of revolutions. There were many absolute monarchs in Europe in the middle of the 19th century. And there were revolts in many countries around Europe. In most countries in Europe, not all, but most, had revolutions in 1848. That was the year of revolutions. And they were put down with a bloodthirstiness and ruthlessness that is just about what Gaddafi's doing right now. And they weren't successful. I don't think, maybe one of them had some success, but basically thousands of people were killed or tortured as a result of those, which may be what's going to happen in Libya, who knows. And then we have this earthquake. Just what we needed at this point, right? How many of you have watched any of the video from there? Any of you seen some of it? Okay, most people. I won't show you then any here because it's so horrible to watch. But if you haven't, you should. What you will see is this front of water that was, I don't know, up to close to 10 meters high, like 20 or 30 feet high in some places, moving inshore as a result of the earthquake. I thought I should say something geological about why that tsunami occurred. And this is my assumption as a geologist. I don't know this for a fact, but the way that these things happen is that in Japan, let's see, for you that's west, okay? All right, so this is a case where the Pacific plate is subducting under Japan like that. So you can picture what happens. It doesn't go nice and smoothly as if it were all greased. What happens is there's a slip and then it sticks. Now try and picture what's happening. The hand on the window side is pushing down and it's pushing down the other side like that, slowly, over hundreds of years because of friction. And finally, the friction doesn't hold and this thing bursts up to the surface. So you can see that this thing is going to be moving up like that, right? So what it does is it pushes up all the water on top of it. And this is a vast area. I mean, it was hundreds of kilometers along the length of Japan. And so when this block of ocean crust rises, all the ocean water on top of it also rises. So it's just instantaneously pushed up, and it's much higher than the water around it. So this wall of water pushes out. And so the westbound water then went right into Japan with almost no warning because the earthquake wasn't that far offshore. The water going the other direction, because remember, it's like you suddenly, imagine your bathtub, you just have a hydraulic jack that can just suddenly lift up. So all this water goes spreading out in all directions. So some of it got here, and I think one person died in California as a result of it. Somebody who went out to take pictures of the tsunami coming in and was, pardon? And got swept, yeah. I think 5 people got swept out to sea, and 2 swam back, and 2 were rescued, and 1 wasn't. Yuli?
I just want to mention that the earliest amount of time I heard from between the earthquake and the tsunami was 7 minutes.
7 minutes. So there's no warning. I mean, I suppose somebody told you right now that tsunami was coming in 7 minutes. What would you do? I don't know. Get to the top of the building and hope it holds, something like that. Yeah, Ryan?
Well, you're mentioning I think the one guy who died was in Crescent City.
I think that's right.
Which is, if you've never been, it's probably not a town you would go out and really see. It's not a pleasant town, but it's kind of a little fishing village up in Illinois County, Arcata, just south of the border of Oregon, maybe by a half hour or so. And the way that the geometry of the California coast works, and apparently there's a submarine ridge that kind of goes out from Crescent City, in the way that their land mass is shaped, and they're just north of the Cable Casino. And the way that all of that kind of comes together, Crescent City is what gets hammered by tsunamis in California. And in 1964, a big earthquake in off of Alaska, I believe, did away with most of the town. I mean, it's probably half the town, and you can go, and there's a visitor center there, and shows you what parts of the town are removed. And it's really an experience to be standing there and realize that this is something that happens just in Japan or just in Indonesia, but this is something that happens in California, albeit a region of California you may have never been to.
Deborah?
I haven't quite understood when the ground pushes up and displaces that water. Is it the energy that moves through the water, or does the water actually push through?
The water actually pushes up. I mean, if you have a suddenly you have water piled much deeper than anywhere around it, the front of it just sweeps out, so it's actually moving out. It's not like a wind. It's not like a wind and a wind wave basically involves the particles in the water moving up and down like that, and the front sort of moves along. But this is actually a front of water moving along. So yes.
I wonder if you were right, there was severe damage in Santa Cruz also. Is there a similar kind of geological?
Not that I'm aware of. I suspect that was due to the shape of the Santa Cruz Harbor. I don't. Historically, Santa Cruz doesn't really have stone.
Yeah, I don't know on that.
Oregon does. If you go anywhere north of Cape Mendocino along the coast up, I think all the way to Seattle, they have tsunami evacuation zones. And then south of Cape Mendocino, it stops. And I think that there's a good geophysical reason for that.
So, as a result, let me start that again. Japan was probably better prepared for earthquakes than any other country. They really have good building codes. People know what they're doing. They're very orderly, and they will follow the instructions from the authorities when it's necessary to evacuate. And so I don't know at this point how much damage was done by the earthquake, because it was so immediately, a few minutes later, followed by the tsunami that just washed things. Have you seen, some of you seen the pictures of houses riding along on this wall of water in flames? Some of them upside down. It's just almost incomprehensible. Yeah, Chris?
Commenting on houses riding on waves. There was a photo of a house that was, I think it was like 100 miles offshore, just floating in the ocean.
100 miles offshore. Oh my goodness, I don't know if you could hear that. There was a house, he's seen pictures of a house 100 miles offshore floating that's been carried out that far and hasn't sunk yet. So, oh yes?
Someone sent me a link to the best video I've seen of the tsunami coming in, and it's 3.5 minutes long, and it starts with the very beginning where the water starts to surge in. Tremendous tide as it comes in, and it rises in that 3 minutes to 30 feet. You see the street fill up.
Mm-hmm.
It's unbelievable, and the house is being lifted away in 3 minutes.
And interesting thing is that tsunami is a Japanese word, and if anybody was going to be prepared for tsunami, the Japanese would have been, because in fact they had seawalls all along there that would have stopped a small tsunami. But this was just such a huge event that you can see in some of the pictures boats that are out in the harbor just carried right up over the tsunami seawall and turned upside down. Matt, were you going to say something? Okay, yes.
Yeah,
Alex?
a nuclear physicist from Berkeley actually toured the nuclear reactors before this.
Mm-hmm.
And apparently the reactors in Japan are the safest and highest rated reactors in all the world, which kind of gives you a new perspective on, if the U.S. really goes nuclear,
Yeah.
we start getting a bunch of nuclear sites.
So let's turn from the earthquake and tsunami, which would have been that would have been the news of all news at this time, but it's being swept aside by the news of the nuclear reactor. Yes, I'm sorry.
Is there any way to predict when the ocean crust will give in and
When the earthquakes will take place?
Is it random?
As far as we know right now, there is no reliable way to predict a particular earthquake. What they can do, and you'll see these all the time, is they can make statistical predictions. So they will basically say there is a 50% chance of a magnitude 7 on the Hayward Fault in the next 30 years or something like that. Okay, that's reasonably safe to say that. But to actually say there will be an earthquake in that spot in Japan on a particular time and date, we don't know how to do that, and there's good reason to think we never will. because it looks like earthquakes start with a little break someplace, and then that break nucleates, and most of the time it goes out, and then it kind of, I'm thinking, imagine this is the plane of the fault right here, and something is going to break, and it breaks here, and it spreads out to a certain point, and all of that shifts, but all the rest doesn't. So the bigger the area that shifts, the bigger the earthquake. And that seems to be something which is chaotic in the technical sense, which means it's unpredictable which little earthquake is going to grow into a big one and which one isn't. So I suspect that we'll never be able to predict earthquakes in that way. We might, but at this point, it doesn't look like it. Yeah?
I was just wondering if you knew how earthquake savvy all the buildings on this campus were, and like in the case of a huge earthquake.
Well, that's something that our previous chancellor, Berdahl, made a big effort. One of the big things that he did during his tenure as chancellor was to really push for reinforcing buildings. So this building was one of the ones that was done fairly early on. In fact, they tried doing it once and decided they hadn't done it right, and so they undid that and then did it again later. So those of us who were in this building had 2 episodes in which we tried to teach while there was jackhammering going on inside the building. It was grim. But at any rate, for example, what's been done on this building is they were concerned particularly about back and forth, because this building is elongated in this direction. So it's less likely to move that way than it is to move this way. And so 3 things were done to this building. On the south end and on the north end, they tore out all of the rooms and offices, and they thickened the wall up to the 3rd floor. So in my office, those of you who come to office hours, ask me next time, but you might have noticed that there's a shelf by the window with a sort of a little metal edge on it, those of you who've come. The reason that shelf is there is because they built a strong wall down to the ground floor up to that particular level. It was felt that the lower 3 floors needed the most reinforcement. And the other thing, some of you, I think when you come to class, you come in that front door, and there's a sort of a stairway up there. That tower that the stairway is in didn't used to be there. And it was built as part of the seismic safety retrofit of this building. So that is a very strong thing. If you look at it, there aren't windows. 3 sides of it don't have windows on it. It's all solid. And it was built as a buttress. I used to think of it as being kind of, this building would be like a drunk leaning on a lamppost, you know, when things start shaking, and that's the lamppost. And then it was tied in by great big metal plates, big thick metal plates, steel plates like that, that are tied in there, and then they come across and they were all bolted into the foundation. So the point is that this building underwent a major seismic retrofit, and many others have since then. For example, if you know Hearst Mining Building, the beautiful building that's up there, that was set and it was put on base isolation, which means that if this is the ground, say, supposing this is the ground, there are these huge cylindrical things that have lots of layers in them that will slide back and forth like that. And the idea is that Hearst Mining will stay more or less stable while the ground moves underneath it, so it won't be shaken down like that. So Bancroft Library has just been done. I think Moffett has been done. South Hall has been done. Many of the buildings on campus have been seismically retrofitted. It's very expensive to do this, and the more work you do, the more expensive it is. So my understanding is that a decision was made that they wanted these buildings to be strong enough so that nobody would be killed in a collapse after an earthquake. And so that's the standard, but they couldn't justify spending enough money to make sure that the building would be usable afterwards. So that's the criterion that was done. So a lot, yeah, in answer to your question, a lot of work has been done on the campus about that. Yeah. Okay, so as if the earthquake and the tsunami weren't enough, now we have the nuclear power plant with 5 different reactors, of which 3 or 4 are in trouble right now. And I don't know what to say about that. I don't really have a position on nuclear power. I have some friends who think that it's an absolutely insanely risky thing to be engaged in as a way of producing power, and that we should stop building we have stopped building nuclear power plants and dismantle the ones that exist. And I have other friends whose view is that coal and oil-fired power plants are much more of a risk, not because they're likely to explode, and if they do, it would be a local thing, but because of the global warming that may be resulting from using that. I don't know what the answer on that is. This event is certainly reopening that debate and discussion right now. One thing that I had lunch with a physicist and the chemist today and got an answer to a question. I really wasn't successful, but the question was this: why are people so scared of nuclear power? Okay, if you think about coal-fired power plants, somebody has to dig out the coal, and every few years there's a coal mining disaster, and some substantial number of miners are trapped below ground and killed. And vast numbers of miners have black lung disease from breathing coal dust all their life. And we are loading up the air with CO2, and as a result there are small island nations in the Pacific that may just kind of vanish beneath the water. Okay, so that is bad. Now, why are we so afraid of nuclear power, of nuclear plants? Well, I suspect the reason is that radioactivity is so scary because you can't see it. You can't smell it. You don't know when you've gotten a dose of it. It's not like you're crossing Hearst Avenue out here. You can look both directions and avoid crossing when a car or a truck is coming. It's something that's insidious, and it's also unfamiliar. We're not used to it. Most people don't spend much time around radioactivity. I certainly don't. And so the people who are pro-nuclear will say that that means that the threat is greatly blown out of all proportion. And the people who are on the anti-nuclear side will say, sure, most of the time it is, but what if you have a really major nuclear power accident? And we may be seeing one happen. We don't know whether the Japanese are going to get that power plant into a safe condition or not. But it's a debate that generates an enormous amount of emotion on both sides, especially the anti-nuclear side. There are more and more of us all of the time. There are more and more people in the planet, and more of the people in the planet feel like they ought to be able to enjoy the standard of living that we have here in this country, which means using a lot of power. Where does it come from? I don't know. These are awfully hard questions. I wish I had answers, but I sure don't. Deborah?
Don't you think that the issue of safe disposal of the radioactive material is a huge one?
Yeah, the safe disposal is a big part of the problem. From my slight understanding of what's going on in Japan right now, a lot of the problem is coming from nuclear waste. That means nuclear fuel that was used and is now pretty well used up, so that it still has some radioactivity, but not enough to be useful in the power plant. And so it's stored, and it's stored in water pools which keep it cool. And that some of those water pools have lost their water because of the effects of the tsunami on pumps and everything else. And so that stuff is heating up because it's not being kept cool, and you might have a leak from that. So that's one of the big arguments about nuclear power here, is what do you do with the waste? So it's really a political problem. There are places you could put it. You know, there's a big area in Nevada that has been under consideration. I'm forgetting what it's called for the moment. But, pardon? Yucca Mountain, thank you. It's in sort of the center of Nevada. Not very many people live anywhere near there. And it's been studied exhaustively to see whether it's safe to put used nuclear fuel down there. And maybe it's not 100% safe, but it's sure safer than leaving it stacked alongside the reactor, which is where most of the nuclear fuel is right now. And the problem is that the people in Nevada don't want it there. You know, why should they have in their state all of the nuclear fuel that was used to produce power in all the other states? And so the head senator from Nevada has blocked that for years. And there's no place to put the spent fuel, so what does it do? It kind of sits there next to the reactor, just as Deborah's saying. So it almost seems to me like you could make the argument that the main problems with nuclear power are political ones rather than engineering ones. Although what's happened in Japan is arguing against that. Yeah, somehow?
I'm sure people discussed about it. How about putting them in a subduction joint?
You know, that's a really good idea. Let me show you something about these things. So, okay, let me draw you a subduction zone. This is going to be, let's say, Japan, since it's the one we're interested in right now. So this is the ocean crust that's going down. This is moving down like that. And here's the overlying side, and here's Japan over here. And there's water across here like this, right? So you can see what happens. This is one where if this sticks, it will get pulled down further and further so that this edge will look like that, and then like that, and then like that. I'm exaggerating. And when it finally snaps, this comes back up. All of this water gets raised up into a big bulge like that and goes out. That's what makes a tsunami. This is entirely out of scale. But the point that Professor Kim raised, which I think is really interesting, is that if you look at that, let me just draw like that. So this is called the trench right here. So this is all water in here, and these are the deepest places in the world. And as deep ones, they fill up with sediment. And the sediment is very young and very soft because, you see, older sediment gets carried down. And so it's only the newest sediments that's there. It's very young, it's very soft, it's like gooey mud, right? So the idea was proposed back in the 1970s that a good way to dispose of nuclear waste would be to go out here and put your nuclear waste into something that sort of looked like a bullet or something like that. So this is all full of nuclear waste at a different scale now. And you make this out of steel or lead or something like that, and you go up here and you just cut it loose, and it goes down and it sinks way into the sediment and just sits there until over, you know, hundreds of thousands of years or millions of years it gets subducted and you never see it again. And so that's a really good way of, would be a really good way of getting rid of it. The political pressure, though, is not to contaminate the ocean. And so in sort of people who have that view without thinking deeply about it would say, well, you're contaminating the ocean by dropping all of this nuclear waste in it. People who think more deeply about it would probably say, well, it goes in there. How can you be sure that it isn't going to heat up and then rise up to the surface? No people live there. You know, there's lots of animal life living there. So it is I think it's probably politically undoable. Can you imagine what Greenpeace would have to say about that? Can you imagine the fleet of Greenpeace protest vessels surrounding any ship that went out there to drop that stuff? So a lot of it's a political problem. Yes, Ricardo, you had a question.
In the case of the Yucca Mountain, what does that mean for future generations? You know?
Well, I think that's what that's the concerns about Yucca Mountain are that if you put all of that waste underground, what they really worry about is waste getting into the groundwater. Well, you're in the center of Nevada. There isn't much groundwater. But as big historians, we have a longer view of that, and it's just like the Sahara, where it's cycled back and forth. And the Great Basin has been very wet. Have any of you ever have you ever been to Salt Lake City and seen Great Salt Lake? There are shorelines carved into the mountains up above Salt Lake City, because Great Salt Lake used to be much bigger than it is in the last wet period. So what they are concerned there is not so much the situation now, but what happens in the next wet phase. And if you have to isolate this stuff for maybe 10,000 years to get rid of the dangerous radioactivity, for it to decay away, that's what people have worried about. Yeah.
Recently a Bill Gates TED Talk where he talked about nuclear power and his kind of idea of the future of nuclear power. And he's invested millions of dollars in this new type of reactor called the traveling wave reactor, which runs on its own waste. So it would cut down on the nuclear waste tremendously. And I think it's also safer as well. So
Well, thank you. I didn't know about that one. I think we could continue about this indefinitely, but I would like to talk about something that's maybe a little less grim for a moment. Deborah, could you hand out half of these for me? Half on one side. So this is a little mind map, and we'll talk about that. 2, 3, 4. Sure.
Did you happen to catch
Professor
Mueller's interview with Bill O'Reilly last night?
No.
I didn't catch it either, so I heard that conversation. I got an email from the class.
Oh, are you in that class?
Yeah, I'm in physics.
Oh, okay. Well, I'll be interested to hear what he has to say. I know he's generally pro-nuclear, but...
Thank you.
Do you want to take some in case nobody's coming in at this point, are they? Yeah. Okay, let's talk about something more pleasant for a change. And let's see, Josh, I didn't keep one myself. Thank you. Good. Okay, so look, let's think about big history. One of the things that we've been doing in this class is just going through what has happened, with the broadest brush, because we can't do any details, but seeing what has happened. We've now been through cosmos, Earth, and life history. And after spring break, we'll be getting into looking at things that have happened in human history. So I think it's valuable for you to have this overview of what has happened in history and all of those different kinds of history. But the other thing that I find really interesting is that I want to think about this. I want to try to understand beyond just the day-by-day events of history. Somebody once said, history is just one damn thing after another. And in a sense that's true, but so one of the things that appeals to me is to try to understand what's going on a broader or a deeper level, let's say. And we've done a little bit of that before, but I just like to play with this. We probably won't get through all of these in the time that's left. But let's think about these things. So if you look at the top, here's some themes for today. David Christen's view, and a number of other people, and I share this, is that one of the most important trends in big history has been the growth of complexity. Now, clearly, we are more complex than the single-celled organisms that were the first life on Earth, right? And Earth is certainly a more complicated planet than the Sun. I mean, it's had all this time to develop all of these intricate little systems. It doesn't put out as much heat, of course, but it's more complicated, more complex. And so the problem with this is, how do you define complexity? If you're saying that in history there is an arrow of increasing complexity, and you're a scientifically oriented person, you want to know, well, what does that mean? How can I measure complexity? There is an astronomer at Harvard named Eric Chasen, who's one of the few scientists who's really been active in thinking about big history for a long time, and he's written a couple of good books about it. And he suggests that complexity can be measured by power density. Okay, for the physicists and the astronomers here, that immediately means something, but let me explain what power density means. If you start with energy, I mean, you eat a certain number of calories of food during the day. That is a certain amount of energy is in that food, right? It's measured in calories, and the package will tell you how many calories, right? Okay, so that's energy. Now, your body uses up that energy at a particular rate. So if you take the number of calories that you eat in the day and divide it by the number of seconds in a day, that would be your power, your energy use rate. And it would be in something like calories per second or calories per day, right? All right. So we've now got two concepts. We've got energy, which is amount of energy, and then we've got the rate at which it's being used up. And those are very familiar. So you buy energy, or if anybody who has a electric meter in their house pays by kilowatt hours. So kilowatts is a power, it's a rate of energy use times the number of hours. So that's the amount of energy used. Okay, well, what Eric Chasen has done is to go one more step, just one more step in this, and say, well, let's see, what is the rate, what is the power, the rate of energy usage per kilogram of weight, okay? And so that's called power density, or it's in the middle left diagram down there, it's also called energy rate density, because power is energy rate, okay? So what he's saying here, and I think this is absolutely clever, I have some problems with it, but I think it's extremely clever, is he says, let's look at how much energy is used up per unit time, per unit weight or mass by something. So if you look at this on the left, you see here are galaxies. He's ordered these in galaxies, suns, stars, planets, and so forth. He's ordered these in the order of their appearance on Earth. So he's got approximate age there, and those are age 10 to the 9th years. So a geologist would have written GA for giga years. Same thing, I'm sorry, billion years, excuse me. And so galaxies would have formed, he's got here, something like 12 billion years ago, with the whole universe forming 13.7 billion years ago. And so they're getting younger and younger down through stars, and then planets like the Earth, and then plants, thinking about the biosphere, and animals, and then our brains, and then society. And he says, what is the rate of energy use divided by the mass of those things? And it was really surprising to me to see that each of us has an energy rate density that's enormously greater than the sun. Can you believe that? You wouldn't have thought about that. I mean, if you think about what the energy rate is, the sun is putting out far more energy than we are. But if you divide by the mass of each one, the weight of each one, it turns out that we put out more. And so look at that. If you look at that, on the right-hand side is the energy rate density. And you can see that if you're used to dealing with these things. The units underneath are ergs, that's energy. S to the minus 1 means divided by seconds. That's energy per second. And then G to the minus 1 means per gram. And so in those units, what you'll see is that a galaxy, even though it's vast and it has these enormous numbers of stars in it, it's only putting out about 0.5 in those units. A star like the sun is putting out 2. A planet like the Earth is putting out 75. I don't know how he measures that. That's the difficulty with this is how you measure it. Plants are putting out about 900. Animals, much more. That makes sense. We're much higher up on the food chain. And then the amazing thing is our brains. Look at our brains, how much more they put out than the sun. Your brain is putting out about 150,000 ergs per second per gram compared to the sun that's putting out 2. So this is his idea of trying to find, and then society is even more when you consider all of the infrastructure that's going on around here and all the computers and cars and things that are running. So this is his idea of how to measure complexity and show that it is increasing through time. I would say this hasn't caught on, probably because I don't think many people have read Eric Chasen's books, and the ones who have read them are mostly humanists, so I don't think this has gotten much consideration in the scientific world. I had a problem with it, and that is there are many different kinds of stars, right? So if you think about stars, there's a wide range of energy density, and maybe it just happens that the sun is one that falls in the right place. You guys and Katie, Paul, you might be interested in playing with that and seeing what stars of different categories put out. Yeah, it was?
I'm wondering about how do we weigh society?
There's some pretty soft numbers in here, I'll tell you. He sort of he has a kind of a rough guess. But these are what are called order of magnitude estimates, you know, and scientists often, when we deal with things that we can't measure very accurately, we say, well, what to the nearest power of 10, what is it? And so this is an order of magnitude estimate. It's also called a back of the envelope estimate, which means that's where you made the calculations, usually while you were having beer and wine in a restaurant someplace, okay? Okay, so I thought you'd find that interesting. So now let's think about something that really fascinates me, and that is thresholds. So this is a word that David Christian uses. And he basically says every now and then in the unfolding of big history, you cross a path from one state to another, and suddenly things are different. And there's several of those within the Big Bang, but remember at the end of the Big Bang, there aren't any stars yet, and so there isn't any source of light. And so this is what we call the Dark Age when we were talking about the history of the cosmos. Okay, now what happens when you have the first stars appearing? For David Christian, that's a threshold. Something new has happened. You know, you've gotten to the point where you have gas that is in such big balls of gas that the weight of all of the outer portions have squashed the inner part until it can react and have nuclear fusion and produce light. Okay, so that would be a threshold. Then, so that would be, let's say that's the start of cosmic history, if you wish, after the Big Bang. Then the Earth is something else that when you start to get solid planets, when there has been enough metals in the astronomer's sense, enough metals generated, the metallicity is high enough that you can have solid mineral grains instead of just hydrogen, helium, balls of gas. Then for the first time you get solids, and in the case of the Earth you get liquids. So obviously Earth isn't the oldest of the solid liquid planets, but it's the one that we know most about. So in the trajectory that leads to us, there's a threshold there when the Earth forms. And then life is something new. I want to talk about that mostly. And then when human prehistory starts and people start using tools and probably language, that's something else. And then when written human, you see there are these thresholds in which big history shifts from one mode to another. It's not a smooth progression. And so I'd like to just tell you something I've been thinking about with regard to thresholds. I've been thinking about them as phase changes. So those of you who are in the physical sciences will be very familiar with the term phase change. So this is for example, this is the change from solid ice to liquid water to steam vapor. And then if you heat it high enough, the point where all of the molecules break apart and the atoms come apart and the electrons separate, then it's called a plasma. So there are 4 phases that physicists usually think about. There are solids, liquids, gases, and plasmas. And so for physicists and chemists, geologists, this is a very familiar concept. We really know how to handle that, how to deal with it. And so I started to think, could we consider David Christian's thresholds to be phase changes? So in the case of going from the dark age, the cosmic dark age, to the first stars, it's definitely a phase change. Because before that, you had gas everywhere. You had hydrogen, helium, gas. And when the first stars start to form, that enormous pressure of the great ball of gas, starting up the nuclear fusion, that nuclear fusion heats those gases up to the point where they become plasmas. So you definitely have a phase change when you go from the dark age at the end of the Big Bang to the beginning of what the astronomers call the stelliferous era, the time of stars. I think it's worth thinking also about the kind of physics and chemistry that goes on in these different situations. And let me bring that in when we come to the Earth. Because when you come to the Earth, you've had a threshold in David Christian's sense, but you also have had a phase change. Because the universe before solid planets, or the universe excluding solid planets, is gases and plasmas. The Earth has solids in it and liquids in it. So it literally has 2 new phases. Those are phase changes that any physicist or chemist would recognize. Any geologist or geochemist would recognize those as phase changes. And so I started to think, could you carry that on and consider the additional thresholds, the beginning of life and the beginning of humanity? Could you think of those as phase changes? And I think my first thought is you really couldn't, because a physicist or a chemist would not think of a living organism as a phase. We're too complicated. A phase would have some extent. For example, there's gaseous phase around you right now. Breathe in some, like that. That phase is extended through this entire room and outside and all the way out to the edge of the atmosphere and all the way down to the ground. So that's a physicist's or a chemist's phase is extensive like that. It's continuous. Whereas if you think about us, we're this mass of cells, and every cell is different and has different things going on. And so I was kind of left with a situation where you'd say, either we should think of living organisms as a new kind of phase, or else we should say that phases don't exist once you get life going. Or if they exist, they must be in tiny little increments because you've got all that biology going on in you. I sort of dread bringing this up to physicists or chemists or biologists. I haven't done it yet. You're sort of the first people to hear about it. But let me show you something here that, I'm sorry, no, I'm going to wait on this just a sec. Okay, so that third point is maybe it would be useful to consider life and humans and brains and societies as new kinds of phases of matter. I don't know, maybe it will or won't. As I've thought about the different thresholds, the different phase changes, if you will, it seems to me like the most radical of them is the beginning of life. I mean, with the beginning of life, you go to something that's utterly, entirely, completely different. And maybe concept of phases isn't even applicable anymore. But let me show you something that's fascinated me. So a week ago, when David gave his talk about origin of life, and he talked about what does it mean to be alive, he picked two aspects, and that was metabolism and reproduction. I think that's what you had in it, right? So in order to be alive, those are two things that you have to have: metabolism and reproduction. And they're and that's absolutely clearly correct. What I'd like to do then is to think about another aspect of what it means to be alive. You could make a list. Sometimes on this class we'll make a list of how many characteristics are there of living organisms, and it usually comes out to be 8 or 10 or 12 or something like that. But I want to focus on another one that has just impressed me so much lately that I want to share this with you. And that is the fact that living cells are bounded by a cell wall or a membrane. And at first that may not seem like a big deal, but here's why I think it is. First of all, that's why we can't, why physicists and chemists wouldn't think of us as being phases. Because we're all these tiny little cells. And what's going on inside that cell is extremely complicated. And in fact, remember I was saying that in, I don't know if I did say this. Okay, I will. When you shift from the phase of the cosmos with plasmas undergoing nuclear fusion, and you come to a solid liquid planet like the Earth, the kind of physics that you deal with and the kind of chemistry suddenly shift. Think about a star. The physics that goes on in a star is this, what is it? It's the physics of gases and plasmas. Gravity is important. Thermodynamics, the study of energy transport, is important. Nuclear physics is important, things like that, okay? When you come to the Earth, suddenly you got a whole bunch of other things. You have fluid dynamics of liquids, and especially you have inorganic chemistry. Think about that. In a cosmos that's dominantly made of hydrogen and helium, chemistry isn't very interesting, right? Because helium doesn't bond with anything, so it doesn't get involved in chemistry, and hydrogen only bonds with one other hydrogen, if that's all there is. So that's not very interesting. As you start to get some more things, maybe you get carbon monoxide and methane and things like that. But basically, the chemistry in the Earth is much more interesting than it is in a star or in the galaxy, because all these complicated things are going on inside the Earth. Think about what happens when the first cells appear, the first life appears, and you have cells. The first thing is that you've got organic chemistry going on. Now, each of you is an organic chemistry reactor going on. You are an incredibly complicated set of test tubes with stuff going on. And I want to make that point with a really remarkable drawing here that I don't pretend to understand this drawing. Some of you may. Some of you who are pre-med, you might understand this. But let me just show it to you because it's incredible. That's Sienna. We'll come back. Let me see if I can find what I wanted to show you. There. Okay, this is what I wanted to show you. So this is an enormously complicated diagram showing metabolism, and Roland, bless his heart, turned it into a zoomable version for me. Otherwise it would be incomprehensible. Let's go out and see the whole thing. So there's the diagram. This is, how many of you have seen this? Anybody seen this? Okay, pre-meds? Biochemistry. Okay, well, you know more about this than I do, but I want to make a point about this. This is the diagram showing metabolism in organisms. And it combines, I think, plants and animals, because there's chlorophyll in here someplace. But you can get the idea there that it's pretty complicated. So now let's go down here, and this is the legend for it, and let me just give you a hint to help you show the thing. So you can see there is pink. So this is a part of metabolism that's called glycolysis, and it goes on in the cytoplasm. What's the cytoplasm? That's the stuff that's inside your cell. You know, your cell has an outer membrane, and it's got a nucleus, and it's got things like mitochondria, but the rest of the stuff in there is cytoplasm. That's about right, I think. Yeah, hopefully. Okay, so that's the stuff that's in pink is. Keep this in mind. What's in pink is happening inside inside your cell. Okay, then there are mitochondria, which are deeply involved in metabolism. Remember, those are those endosymbionts that Lynn Margulis discovered. Okay, so there's stuff going on there. That's shown in yellow. That's something called the TCA cycle, which is mainly in the mitochondrial matrix. That's the inside of the mitochondria. But part of this stuff is also going on in the membrane that separates the mitochondria from the rest of the cell. I hope I'm getting this right. If I'm not, I apologize. But so pink is the cytoplasm, yellow is the mitochondria, and green is the cell wall of the mitochondria. Okay, so let me go back out. So you can sort of see it here now in the general view. See, here's pink down here. So this is what's going on in the main part of your cell. Then yellow is the interior of the mitochondria, the mitochondrion, and then the green around here is the cell wall. Okay, the point is not to explain this to you, which I would not be capable of doing. The point I want to make here is to show you just how complex the chemistry is that can go on inside each cell because the cell is bounded by a wall. Yeah?
I was talking to my professor about diagrams like this, and in reality, this is only a small fraction of the metabolism that's actually.
Wow.
We can't pretend that we mapped out the entire metabolism of the human body. This is what we're starting to figure out.
I appreciate that, and that just makes the point all the stronger, doesn't it? I was afraid you were going to say that this was inaccurate or wrong or something like that, but I'm glad to hear that this is only part of the story. But just look what happens now if you zoom in on part of this. So here we're zooming in, and this is shown in such a diagrammatic way. But remember, this is in the main body of the cell itself. The green is the cell wall, and then this is the mitochondrial wall, and this is the center of the mitochondrion. And this thing here, this cycle is I think it's called the citrate cycle. At any rate, this is a fundamental part of what goes on in the energy use that happens. Okay, so just look at that. I mean, you just kind of zoom in at random, and this is I put a link on it on here so that you can go and play with it if you want to. But the point is not to worry about the details here. The point is to say you have probably 10 trillion cells, maybe as many as 50 trillion cells in your body. This is going on inside every single one of them. You believe that? Think about it's the cell wall that makes it, or the cell boundary, the membrane around it that makes it possible for all this intricate chemistry to be going on inside each cell. If you think about the way things work on Earth, think about some organized system on the Earth. I'll take this off so it won't give you. Okay, think about some organized system on the Earth. How about a hurricane? So a hurricane has some aspects of a living organism. It doesn't have all. It takes in energy, just like we do. We take it in from food. The hurricane takes it in from sunshine and from hot water in the ocean. And then we are organized into particular patterns. So is a hurricane. It's organized into a great swirling thing with an eye in the center. We move like this. The hurricane moves around. So the hurricane does some of the things that a living organism does. One thing it clearly doesn't do is reproduce, although sometimes there will be little substorms that branch off it later, but it doesn't reproduce itself as we do. But I've been more and more struck by the fact that it is an unbounded system. It has no walls around it. So in the center, it's most violent. You go out further and further, the winds get to be less and less intense. There's no boundary between it. You can't say where the hurricane stops and the normal atmosphere begins. And the chemistry, there's very little chemistry in it, and the phase changes are pretty simple because what's happening is that surface water of the ocean is evaporating. It's getting hot, it's evaporating, it's turning into vapor, and then someplace else it's turning back into water and falling as rain. So the point is, this is a simple system on Earth. And it has to be simple because it's not bounded. And life is made of cells which are, and so all this complicated stuff can go on. So when you take your collection of cells and you go off and do whatever you're going to do in spring break, have a wonderful time and think historically about what you're seeing. Historical mindedness.